Bismillahirrahmanirrahim. In this video, we'll be discussing example 3.1 from Power Electronics, book by Mr. Rashid. And this is the question that we'll be discussing. We have to find, for this given circuit, this is the half-wave rectifier circuit, we have to find the performance parameters. And these are the performance parameters, not all, some of it. The efficiency we have to find, and then form factor, ripple factor, etc. So we'll deal one at a time. Now keep in mind that in case of a rectifier, we had already discussed in my previous video that this has two components. The output has two components. One is called the DC component and other is called the RMS component. And where from this RMS components come, it is primarily from the ripples. If we analyze this signal, if we analyze our Fourier analysis, we can see that this has two parts. One is the DC part, DC component, and other is the sinusoidal component, which consists of sine, cosine, etc. So these are basically various harmonics of the sinusoidal signal. And these are the low frequency unwanted AC components or the ripple components. And we can call this as VAC. Now this diagram we had already discussed earlier also, that VDC is this green line, 0.318. VRMS is the red line, 0.5 VM. And this is V maximum, but we can't pinpoint where is VAC because these are the ripple components not visible here. One more thing, as we discussed, we have to keep in mind that when we are on the transformer side or before the diode, we have full AC signal, a full sinusoidal signal. And after the diode, we only have half of the wave, that is positive half in this case. Now the RMS value near the transformer, or the first part, will be V maximum divided by under root 2. But in the second part, VRMS has the different formula. It is Vm over 2, not Vm over under root 2. Vm over 2, which is 0.5 Vm. And VDC, I hope you remember, it is Vm over pi. Okay, with this background, now we'll find the first term, that is called the efficiency. Efficiency is defined as PDC over PAC, DC power over AC power. And since there were two types of signals, DC and AC, therefore there will be two types of power or two powers, PDC output and PAC output. The efficiency of a rectifier is a rectification ratio, not power efficiency. So keep in mind that although we are using the power formulas here, it is a measure of quality and permits us to compare effectiveness of the rectifier. Now, how do we calculate PDC, VDC into IDC? In our case, we are calling it VODC, and IODC will be the current through this resistance when we are applying VODC. VODC is 0.318 and current will be VODC divided by R, that is 0.318 Vm over R. So this is PODC. Similarly, PAC is VORMS into IORMS. Now we are here, remember, this is our VORMS, 0.5 Vm, And when 0.5 Vm is applied, the current will be called 0.5 Vm over R. So this is PAC. And the ratio of the two will give us the efficiency. So it will be 40.5% if we solve this. Just for your information, in case of a full wave rectifier, the efficiency increases and it is all a double to the half wave, that is 81%. Next is form factor. The form factor, it tells if there is any difference between average and RMS value of any rectified signal. If you see here, we have three different outputs. For sinusoidal, we have these two. For square periodic, we have these two. And for triangular periodic, we have this. Now, all three have different values for RMS and average. Now, this is 0.7 and 0.63. These are the same value peak. This is 0.57 and 0.5. So to compare, we use this definition that form factor is VRMS over VDC, and in case of an AC signal or half wave rectifier, VRMS is now 0.5 from here and VDC is 0.318. So form factor ratio is 1.57 or 157%. Next is ripple factor. Ripple factor is defined as the ratio of the RMS value of the AC component in the rectified output to the average value of DC rectified output, both in terms of voltage. VAC RMS divided by VDC is the ripple factor. Now, what is VAC? We don't know. As we discussed earlier also, we know DC, VDC, we know VRMS, we know VM, but we don't know exactly where is VAC. So for that, as we discussed, that the sinusoidal components, they form the VAC. And there is a formula derived in the book, that is VAC RMS is equal to under root V square RMS minus VDC. Now dividing this by VDC and solving, we get now this term square minus 1. And in the previous slide, we have derived that VRMS VDC is form factor. So this will be the formula that we can follow. And form factor we had derived in the previous slide is 1.57. So we'll put this value here. And so ripple factor will be 1.21 or 121%. The next is called the transformer utilization factor. It's defined as the ratio of DC power output divided by effective VA rating of the transformer. Now, the VA rating of the transformer is actually secondary voltage multiplied by secondary current. And from here, we had already discussed that in this case, the secondary voltage will be VRMS, that is Vm over 2. So PDC, VSRMS, ISRMS. PDC we have already calculated. Voltage multiplied by current. VRMS, as I mentioned, we'll have to take this value, Vm over under root 2, but I will be same throughout. So for I, we'll use VO RMS divided by 2. So from here, VS, IS can be calculated as the VRMS and the current. And so this is VS RMS. And now TUF we can calculate by putting the value of TDC and VS RMS. So it will be 0.286. Now the next question is PIV, or called peak inverse voltage of the diode. So how much is the inverse voltage applied? In the forward bias, the diode is conducting, so no inverse voltage. But in the reverse or the negative half cycle, this will behave like an open circuit. So the maximum negative will be applied, and maximum negative is just like maximum positive, or the peak is Vm here and Vm here, or minus Vm you can call. So the peak reverse voltage or blocking voltage is equal to Vm. The next question is called the crest factor of the input current. And the crest factor is defined as the ratio of the input peak current as compared to the RMS value. And we know crest is the peak. CF is IS peak and IS RMS. Now we know how to calculate IS RMS. We have done previously from here. VS RMS divided by R, but IS peak will be what? If this peak divided by R, so VM peak divided by R will give us IS peak, and IS is IU RMS, VU RMS over R, so this is the value, and dividing, the answer is equal to 2. And finally, the input power factor. Power factor also I had explained in my previous video. If you use power triangle, this is the real power, imaginary power, and apparent power. The apparent power can be written, or the real power can be written as P into S cosine theta. And from here, cosine theta is power factor, so power factor will be P over S, where S or the apparent power is V RMS into I RMS. We'll use that. So in this case, in our case, it will be PAC over S. PAC we know how to calculate, and S is VS RMS into IS RMS. But this is for the transformer VA. PAC we had already calculated using this formula. And VSIS also we had calculated using this formula. This is the secondary RMS voltage, and this is the current. So plugging in both the values, the power factor will be 0.707. I hope you have been able to follow this. Please let me know through your comments. Thank you.